So here is another model covered in our book, an application in biology of how an integral can be useful. So this one's about cardiac output, which is the volume of blood pumped by the heart per unit of time. So to measure it, what they do is inject dye into the right atrium, and it flows through the heart into the aorta. And you can insert a probe into the aorta that measures the concentration of the dye leaving the heart at equally spaced times until the dye has cleared. So you're tracking the dye. The dye is like a tracer. So some terms here. C of T will be the concentration of the dye at time T. That would be measured in milligrams per liter, let's say. That's going to probably change, right, as the dye gets processed through the heart. F is the flow rate of the blood, which could be measured in liters per minute. And A is the amount of dye, which would be a constant, right? This would be, they would inject a certain amount of dye. You would know that going in. So you would know how much dye should have flowed through the heart. And so then the actual amount of dye would be the product of the concentration times the flow rate times the time interval, right? We're going to keep track of the concentration at different time intervals. And to see why that's true, it's helpful for me to think about the units. If I multiply milligrams per liter times the flow rate, which would be in liters per minute, so liters cancel, and then multiply that by a change in time, which is in minutes, hopefully you can see not liters, but milligrams would be left over, okay, which would be the amount of dye that was injected. So that's our formula. Now, what would happen is you would be measuring the concentration at equally spaced time intervals. So you could get a sense if the concentration is higher, it might be higher at different time intervals, but you want to have equal time intervals so you're comparing the same blood flow at different times. And so what you would be tracking then is your concentration at a certain time times whatever the cardiac output is times the change in time, plus the concentration might change here, right, at a different, in our next time interval, but the flow rate would in theory be the same, and you would have an equal time interval. And you just continue this process for different time intervals, measuring the concentration, assuming that the flow rate stays the same. So as always, as we've been discussing, anytime you want to add up a bunch of things, an integral can do that work for you. So we could think of this then as integrating from 0 to some time period, the product of those three things, the concentration times the flow rate times our change in time, which becomes an infinitely small dt. The flow rate, again, will assume to be constant, so that could be pulled out. So A is equal to F times the integral from 0 to t of the concentration. So if we wanted to solve for the flow rate, which is what we want, the cardiac output, we can just divide the integral. It would be A divided by the integral from 0 to t of the concentration. So an example using this formula, this is number 11 from our book. They're describing what's happening. They're going to put a dye, inject a dye. It's going to dilute over time. And so there's a known amount, right? This would be your amount of dye. That's A. This is A. And we're going to then keep track of the dye concentration at various time intervals. And someone modeled it. I don't know how you do this, but if someone came up with a model that would predict the concentration at any time t, I would imagine this would get smaller as t gets bigger. The dye concentration will go down. And we're going to track the dye concentration from 0 to 10 seconds, and with that, get an idea of the cardiac output. So using our formula, we have F equals A, which was 6, over the integral. We're going to integrate this concentration formula all the way throughout the 10-second interval. And hopefully you spot, using your integration techniques, that this is going to require integration by parts to integrate that. So I let u equal 20t. dv's got to be the rest of it then, the e to the negative 0.6t dt. Your du is just 20 dt. Remember, your antiderivative of e to a constant t is e to your constant t divided by your constant. That's just chain rule in reverse. Or you could do a u sub to prove that as well if you want to. So using my formula, uv minus the integral of v times, this would be du, we get this messy looking thing here. I'm just going to leave that as it is. Here, what I decided to do was pull out the 20 divided by the negative 0.6. If I pull that out and there's already a negative there, this will now be positive, leaving me with just e to the negative 0.6t. That I just left there. We've already integrated that, e to the negative 0.6t divided by negative 0.6. Once I've done my entire integral, I need to evaluate that from 10 to 0. I chose to do a simplification. This is optional, but the way I saw it is I saw a bunch of stuff that looks the same between these two terms. I saw 20 in both terms. I saw a negative 0.6 in the denominator for both terms, and I see an e to the negative 0.6 t to both terms. So I factored that out, which if I take that out from this first term is just going to leave me with a t, and if I take all of that out from the second term, I'm just left with 1 over 0.6. And it just made it seem a little bit easier. I didn't show the calculation, but if you plug in 10 here and here, and then subtract what you get by plugging in 0 here and here, in other words, using the way we evaluate integrals we've been doing for a while now, I got an answer of about 54.58. Remember, that was the answer to the denominator, the integral of the concentration. So back to my formula for cardiac output, I would have to go 6 divided by that. And I got 0.11 a liter. Now this would be in liters per second because our unit of time was in seconds. I don't know if this is standard or not, but back how they defined flow rate, they had it in liters per minute. So I went ahead and converted that. To convert liters per second into liters per minute, you just need to multiply by 60 seconds per minute. Seconds cancel. I got a final answer of about 6.6 liters per minute as our flow rate.